wish to thank the organizers for organizing such an interesting and multidisciplinary conference in such an amazing and historical venue, and for inviting me here. So, the talk is about inhomogeneous multi-carrier superconductivity as lanthanum aluminate or titanate interface with strontium titanates. So, this is a summary of my talk, and I'll first give a glance at the structure of the interface, and then I'll discuss some experimental facts and our interpretation and try to convince you that these systems are inhomogeneous. Then I'll discuss superconductivity and the interplay with superconductivity and nanoscale inhomogeneity in the system. And I'll show you that effective medium theory successfully describes transport superfluid density and especially tunneling. I will concentrate my talk mostly on tunneling, which is the latest result I have, so it's quite new. And then, if I have time, I'll go through a model for non-homogeneous multi-carrier and multi-band superconductivity, and if time is left, with quantum criticality as further evidence of inhomogeneity. So let's first of all look at the system we are talking about. This is obtained stacking two insulators. On top I put lanthanum aluminate, for instance, and here I have strontium titanate. At the interface between the two, there is a polarity catastrophe. I have an expanded view here. So, while strontium titanate is made up of neutral planes, lanthanum aluminate is the result of stacked planes with opposite charge, +1, -1, +1, -1. This causes a polarity catastrophe at the interface, which may be cured, for instance, if an electron is half an electron per unit cell is transferred from the topmost layer down to the interface. As a result, I have transferred half electron per unit cell at the interface, and this is a possible, though not thoroughly accepted, mechanism for the formation of the 2D electron gas at the interface. As a result, however, experimentally, I have a 2D electron gas formed at the interface between lanthanum aluminate or titanate and strontium titanate, and what is really important is that the density of this 2D electron gas can be tuned by gating. So by applying a gate voltage here, I can change the density of the 2D electron gas. So, experimental fact. The first is the observation of this two-dimensional electron gas. The system is metallic and is the result of stacking two insulators. At the interface, you have a metallic 2D electron gas. The second important evidences for electron inhomogeneity at the interface, there are quite several papers. I'll just show you a picture obtained by piezo force microscopy here. So you see, this is a picture. This scale here is of the order of 100 nanometers. So you see the inhomogeneities which are obtained with contrast on this scale here, show on this nanometer scale. The size is of the order of 100 nanometers here. And if I reduce here the gating voltage, I reduce the density, and you see the contrast diminishes. So this inhomogeneity seems to fade when you reduce the density of the 2D electron gas by gating. And finally, the most, in my opinion, interesting property of these 2D electron gases that they exhibit gate-tunable superconductivity. So as I'll show you, there are quite several papers on this issue. I start from low density, negative gate voltage. I increase the gate voltage, which means increase the electron density at the interface, and gradually the resistance curve show this downturn, and finally you enter in the superconducting state, zero resistance state at the interface. Gate tunable. This is amazing because you can tune superconducting transition with gating. Except that this transition temperature is quite low, below Kelvin, it's 200 millikelvin. but you have here an evidence of a system that can be tuned superconductor by gate. So what is interesting, in my opinion, with these curves is that you see a very broad transition here, much broader than you could, by any theory I know of superconducting fluctuation, try to explain with superconducting fluctuation. And what is more important is a curve like that. You see? You have a sizable drop in the resistivity, but you never reach the zero resistance state. In my opinion, this is an evidence that the superconducting transition here is of the percolative, as a percolative character, and the system is inhomogeneous. It's like in Sigrid's seminar this morning, we have an onset of the superconducting transition and then a broad transition ending or not ending in the percolating superconducting system. So I'll try to convince you that the superconducting state is inhomogeneous, and then the resistance, superfluid density, and family spectra are well described by an effective medium theory. And then I discussed multi-transport and multiple quantum critical theory. Collaborators for the theory are in Rome, in Trieste, and Cottbus, and for the experiments are in Paris and sample preparation in Campur. So, all effect measurements reveal two kinds of carriers at the interface, which are different by their mobility. We call them low mobility carrier and high mobility carrier. And what is definitely shown is that high mobility carrier appear here at a certain voltage which coincide with the gate voltage where superconductivity develops in the system. So it seems definitely proved that superconductivity is related with the appearance of high mobility carriers in the system here. The density of the high mobility carrier, though, is much smaller than the density of the low mobility carrier. So you have to imagine that there is plenty of low mobility carrier in the system which are not superconducting. And then this tiny fraction of high mobility carrier brings superconductivity about. The way we describe the system, it will be clearer in a moment, is that we have superconducting puddles embedded in a metallic background, possibly weakly localizing metallic background. The metallic background hosts only low mobility carrier, whereas locally we have regions with slightly larger density that host both low mobility and high mobility carrier, and those puddles are superconducting. So how does this work? Imagine I have a distribution of critical temperature here, which is the result, say, of microscopic disorder. And then you have a fraction W of the system that can become superconducting, and a fraction 1 minus W, which will never become superconducting. So imagine I start from high temperature here. The resistance is the high resistance of the high temperature state, and you have no superconductivity in the 2D electron gas. Then I start lowering the temperature, so I'm here. All the puddles with a superconducting critical temperature higher than this temperature here appear. They nucleate in the system. And so the resistance drops. I go further down with temperature. I'm here now. I have more nucleating puddles. I'm here. Further down. More nucleating puddles. But if, as this is the case here, when I'm down to zero temperature, I have no percolating path, you see here, then I don't reach the zero resistance state. So it's a matter of percolation, reaching or not reaching the zero resistance state. What is more important here is that by fitting this curve with the effective medium theory, I'll give you in a while the formula we use, you can get the average critical temperature of this distribution and the width of the distribution here. They are simply related to the characteristic of the resistance curve, because usually in effective medium theory, quite generically, the average UTC coincides with the inflection point of the resistance curve, and the width of the distribution is directly related with the width of the resistance curve. So it's very simple. This is the formula you can obtain with a Gaussian distribution of critical temperature. I recall that W is the fraction, the volume fraction of the system that can become superconducting, and 1 minus W will never become superconducting, so it takes its resistivity, which is the high temperature resistivity, all the way down to 0 temperature. There is, of course, a residual dependence on the resistivity of temperature, but this is very weak because it's logarithmic. It's really weak localization, so you can neglect this. So, the dots hardly visible because my experimental colleagues did a very good job, so it's very, very dense. The dots are the experimental data, and the dashed lines are our fits with effective medium theory, and the fit is pretty good here. And we can extract, for instance, the fraction which drops when the gate voltage is reduced, while the width of the superconducting critical temperature distribution stays nearly constant and then increases when the system becomes metallic all the way down to 0 temperature and does not even show or exhibit any attempt to nucleate superconducting regions whatsoever. We extended our effective medium theory there to describe the superfluid density. Superfluid density has been measured at the lanthanum aluminate interface with strontium titanate in this paper here. And the results are shown by the empty circles here. I think I have, yes, a better and enlarged view here. So you see the experimental points. The curve resembles the BCS result, but not quite. They don't fit. So the author of the experimental paper were inclined to describe this deviation from the BCS behavior with a tendency of the system to strong coupling. Moderate, but tendency of the system to strong coupling. I show you in a while that the system is rather in the weak coupling BCS regime for superconductivity, and the deviation are fully accounted for by our distribution of critical temperature. If you enlarge the BCS curve, where the distribution of critical temperature with effective medium theory, you obtain the fit here. The dashed lines are again our fit. Again, we have a fraction of superconducting paddles that decreases all the way down when the gating, which means the density of the 2D electron gas, is decreased, and the amplitude, the width of the distribution of PC, which increases slightly, and then we have a large error barrier here in the fits. So now I come to the very latest result. This is not yet published, it's on the archive, it's submitted. And we have tried to apply our theory to very recent metal insulator superconductor tunneling experiment. The metal is a gold electrode on top of the lanthanum aluminate slab. The insulator is the lanthanum aluminate slab itself, and then the superconductor is the 2D electron gas. The point here is that the gold electrode has a width of the order of several tens of nanometers. So in our opinion, it averages over the distribution of paddles, which is on the nanoscale, of several tens of nanometers. So the curves, the experimental curves are here, and the authors of this paper claim that this is a pseudo-gap behavior in this sense. Look at this curve here, minus 300 volt. This corresponds to a curve where, down to 0 temperature, the system will not exhibit at 0 resistance state. Nonetheless, they say, you have a gap in the tunneling spectrum. So, the system exhibits a pseudo-gap like high TC cuprates. Our interpretation is completely different. So, this shows that you have starting nucleating some superconducting, or at least gap region here. Nonetheless, since they do not percolate, you have superconducting like the EDBU characteristic without having a 0 resistance state. And as you see, the fit we get all the way down from high density to low density is very, very good. We used this formula here. So tunneling characteristics are described by the standard formula where G0 is usually a measure of leakage currents or something that shouldn't be there, but is there usually in the experiments. And then you have this density of states convoluted with the derivative of the Fermi distribution function. And for the density of state, we adopt an effective medium theory form. So we have a 1 minus W fraction with constant density of state, metallic. Then we have all the particles that have not yet become superconducting at the temperature T, which still provide a background to the spectrum, and only the particles that have become superconducting at a given temperature T give a superconducting line shape here. The experiments force us to divide this gap state into two components. One which is majority, which has full developed coherence peak, so the fully BCS density of state form, and the minor fraction X, where the gap is formed, but you have no coherence peak outside the gap whatsoever. In our interpretation, those are particles that are too small to exhibit phase coherence. So they are gapped, so there is a solution of the BCS equation inside the particles, but they are too small to exhibit phase coherence. But they are a tiny fraction, but they are there. For the gap, we use the BCS. Nothing more, nothing less. And here, we have the average critical temperature and the weight of coherent and incoherent fraction of particles. And those here are a few graphs of the distribution of critical temperatures in the system. When we attempted to fit the data at finite temperature now, fixed density, fixed gate voltage, and finite temperature, with T-independent fitting parameters, the agreement is qualitatively good, but not as convincing as the agreement with the low temperature measurements. But the data show that forcing the system to have temperature-independent fitting parameters is too strong a constraint. Actually, we are not inclined to take temperature-dependent distribution of critical temperatures, because we would like the distribution of critical temperatures to be fixed by the physics at high temperature. Nonetheless, if we allow the particle fraction to increase with temperature and then saturate, then immediately you see the agreement is perfect. What does this mean? Now imagine that you start nucleating superconducting particles in a metallic background. As soon as the superconducting particles nucleate, by proximity effect, they tend to induce some superconductivity in the metallic background, so that the fraction of the system that exhibits superconductivity increases with lowering the temperature, and then it saturates. By this, simply by this, all the other parameters of the TC distribution are fixed at all temperature. We immediately have a good agreement at negative gate voltage, zero gate voltage, and positive gate voltage here. So, how many? Okay, so this I can go through. So, how do we describe now this on a more microscopic level? So far it was phenomenology, nothing microscopic, nothing. Now, imagine that you have a subband structure which may, for instance, this is not necessary, originate from the fact that at the interface I have a quantum well that confines the two-dimensional electron gas at the interface. In this quantum well, the levels of the 2D electron gas are quantized. This is a possible origin of this subband structure. It's not necessarily the only one, but I'll take this one just as an example. So imagine that you have low bands hosting the low mobility carrier, and then you have a higher line band that hosts the high mobility carrier. Imagine that somewhere in the system, you only fill the low mobility carrier bands, but somewhere else, you have the density large enough to fill the high mobility carrier bands. Then what happens? In this region, you will have superconductivity if the high mobility carrier bands supports BCS. Okay. So we start with multi-band BCS Hamiltonian. Very simple. So we have several bands. We take just two. One hosting the low mobility carrier and the other hosting the high mobility carrier. And we take intraband and interband pairing. To account for the phenomenology of the 2D electron gas at the interface we are studying, we are led to consider this limiting case. The coupling in the low mobility carrier band is negligible. Take it as 0. The coupling between the low mobility and the high mobility carrier band is less negligible, but still it gives a small contribution, so we neglected to keep the smallest number of parameters possible. Of course, as soon as the high mobility carrier band becomes superconducting in the paddles, also the low mobility carrier will. But this is a tiny effect. And then we have the superconducting coupling in the high mobility carrier. And we have, of course, the condition that the energy of the carriers should be in the window of h bar omega naught, where omega naught is the characteristic frequency of the pairing mediator. For instance, the phonon, as I'll show you in a while. So we get immediately this nice picture here, where as soon as the chemical potential enters the high mobility carrier band, the critical temperature starts to increase. But only when the chemical potential is fully in the high mobility carrier band within a range h bar omega naught, then the critical temperature saturates to the well-known BCS value. So we have two results. One, that we fit the experimental data as extracted from the, say, effective medium theory fit of the resistance curve. But more important, the width of the region where the critical temperature is an increasing function of the density is directly related to the width, the characteristic frequency of the pairing mediator. It's a direct measure, because as soon as the chemical potential is distant from the bottom of the high mobility carrier band more than h bar omega naught, then the superconducting critical temperature saturator constant, the BCS value. By that, then we can extract the Debye frequency, which is 25 milli electron volt, typical phonon frequency in the strontium titanate, and the coupling, which is 0.125, a weak coupling value. So we are in the BCS regime here.
So this is the average TC, no? This
Yes.
is the distribution.
And then, for instance, you may say that there is a distribution because locally you have more or less microscopic impurity with some Finkelstein formula. You can imagine that.
How could you go to the high energy, high temperature Taylor distribution? This one. Yeah, in the sense that you had the distribution of the TC in the fit of the tunneling, when the maximum TC was 0.6
Yes.
Kelvin. So why you should have coupled to such high local TC?
Well, one possible explanation is that we have not figured this out, but we have several evidences that the temperature in the paddles may be even much higher than the temperature in bulk strontium titanate. This may be caused, for instance, because when you have the confining potential, you have enhancement in the density of states. So it's BCS, so a slight enhancement in the density of states gives you a strong enhancement in the superconducting critical temperature. It's as simple as that. How much? 5. I'll try to get through quantum criticality then. Okay. So, the measurements have been performed in Paris, and they are as simple as that. I take now the 2D electron gas, which is superconducting, and I kill superconductivity by a magnetic field. I show you what I get here. So I start from a curve like this, at 0 Tesla. I increase the magnetic field, and I end up with a curve like that in resistance. So I kill superconductivity. If I look to the curves, they are characterized by flat portions at two different values of the resistance in two different temperature ranges. There is a higher temperature range where I have an almost constant resistance curve here, and the lower temperature range where I have an almost constant resistance here. This is much better seen. These are enlarged views just to show how flat is the resistance curve there or there. This is better seen where now I draw the isotherms, and the isotherms cross at the magnetic field. Crossing of isotherms means constant resistance with temperature. Very simple. So here, I obtain two characteristic values of the magnetic field, Bx and Bc. This at higher temperature, and this at lower temperature, in the higher temperature range, in the lower temperature range. In correspondence of both, we have scaling, full scaling, which means that the system is exhibiting a sort of quantum critical behavior, though the scaling at higher temperature is characterized by an exponent 0.66, while the scaling at low temperature is characterized by an exponent 1.5. So we change. We have a crossover between two different quantum critical behaviors. Of course, the true, possibly true, quantum critical behavior is the lower temperature one, of course. The other is just a crossover when the system behaves in a different way. And why is this so? This is so because we have the paddles here. This is just a plot of Bc and Bx as a function of gate voltage, which means density. And you see that Bx rises and then goes to a constant value, whereas Bc closely follows the critical temperature with a factor, a conversion factor of 1 Kelvin for 1 Tesla. Very simple. Acceptable. Why is it so? It's so because we have the paddles in the system. So imagine that you have a critical field to kill superconductivity within the paddle. We call it Bx. But when you get there, you realize that the paddles are not isolated. They are embedded in the metallic background. And the metallic background mediates pairing between the paddles. This is just because the Cooper susceptibility in the metallic phase is fine. So it mediates pairing with the other paddles. So the paddles get phase locked, and you need an extra magnetic field to kill superconductivity in the array of paddles. And this explains why we have two critical magnetic fields. At the level of a single paddle, the system is homogeneous. So you simply need to kill superconductivity within a given paddle. However, when you go to the system or to the array of paddles, you are now in a disordered landscape of paddles, so the exponent zeta nu has to obey the Harris criterion for disordered system, which means that it needs to be larger than 1, and this is why we found 3 outs for the exponent there. I'm done, so this is just a view of what is happening here. We start from a temperature. When the coherence length, the correlation length increases, you start locking the phase within the paddles, and then you lock the phase between different paddles. And so you have a crossover when this phase length equals the average size of the paddles, which allows us to estimate that those paddles are typical sizes of 100 nanometers. So we have a good estimate with which these are my concluding remarks here. So we've also attempted the multi-carrier magnetotransport fits of the data within effective medium theory, and this gives very good results. So we can improve the interpretation that high mobility carrier and low mobility carrier coexist. We rather say that low mobility carrier exists throughout the system, whereas high mobility carrier are only present in the paddles. With this inhomogeneous picture, we get better fit for the experimental curves. We have also proposed the mechanism for electron inhomogeneity. There are several possibilities. I have not discussed those here, so if you have questions, please. And we are recently analyzing the quantum Hall effect in such an inhomogeneous landscapes. There are several interesting preliminary results, but so preliminary that I cannot discuss them here now. If you have questions, please, but I cannot show any reasonable picture. So I thank you for your attention.
Very ample time for questions, so I have
so I have a quick question. So you propose that you have this Hildebrand phase because of some percolation, right?
Yes.
But my question is, why you assume that you don't have any type of phase fluctuation that also could have this type of effect, like vortex physics or something like that? So why you think think that you have a percolation instead of phase fluctuation to induce some cellular phase?
Well, because numbers are unreasonable. If you try to fit with some paraconductivity, say as Lamazzo platinum or whatever, this drop in the resistivity, you get totally unreasonable number. Of course, you can fit. The fit gives you just a number, but then you have to think about the meaning of the fit you get.
Okay, so you try, but then you find
Yes. The usual as Lamazzo is a tiny portion of that huge width of the superconducting transistor. It's really huge. It's comparable to PC itself. So nothing of the sort you can get by as Lamazzo flat.
I wonder if you couldn't add to your evidence that the mechanism that you're proposing, if in a single sample you use gates to change the aspect ratio of the width to the length of the 2D electron gas.
Oh, that's an interesting question. Actually, to fully, we have used effective medium theory. Effective medium theory is an infield theory. It works very well. It was a work we have done in collaboration with Lara. It works perfectly well if you have no spatial correlation. As soon as you have spatial correlation, then effective medium theory performs not well, let's say. It might be good or not. So our interpretation is instead that there is spatial correlation in the superconducting cluster. So the spatial superconducting cluster is rather filamentary because you have long tails, and you have long tails close to percolation only if the percolating cluster is rather one-dimensional. Otherwise, you have no tails close to percolation.
I'm sorry, I have to stop the discussion here. Too many questions, but we'll definitely continue during the coffee break. Yes, thanks.